So we are overall talking about particle kinematics in a non-rotating coordinate system.
Oh, I did have.
Oh, okay, yeah.
For question 2, for the y component, is it in the radians or?
Look.
That's in the particle kinematics.
Okay.
It doesn't know.
Particle kinematics. This one?
Yeah.
Oh, okay. So anytime you're dealing with derivatives of trigonometric functions, it has to be in radians. So the only thing you can do with trigonometric functions in degrees is just calculating the sine or cosine or tangent or whatever. If there's anything beyond that, then it has to be in radians. Okay, so it's radians, yeah. Any other questions? All right, so we are in particle kinematics in a non-rotating coordinate system. And we're in the middle of talking about the chain rule. And the chain rule says if you know the velocity vector as a function of a position. This is a little different wording than I used last time. The one I used last time is fine, but this is fine too. As a function of a position component, let's say. Then the acceleration is going to be the derivative of that velocity with respect, so let's say the position component, let's call it s. The acceleration is going to be dv ds times ds dt. And the thing you have to notice is that this is a velocity component. Okay, so for example, if you know that the velocity as a function of y is equal to 2y negative 5y, then the acceleration as a function of y is equal to dv dy times dy dt, and dy dt is this. So this is equal to 2 negative 5 times negative 5y, and so you get negative 10y positive 25y. Okay. Rather than knowing right off the bat the velocity is a function of a position component like this, it would come up more often that you're given a position relationship between the two components or the three components and the speed. Okay, so often instead of being given velocity as a function of, let's say, x, you'll be given a relationship between x and y. A relationship between x and y is just a function, right? So you could be given the function that this thing is traveling along. So this is a function the particle travels along. And the speed. Okay, so how do you do that? So for example, let's say that we know that this particle is moving along the function, y equals x squared. Well, the function y equals x squared is just a shape in space, right? So this particle could be moving to the left along this parabola or to the right along this parabola, right? So you need to be given that information. So let's say it's in the direction of increasing x. And for now, let's say that it has a constant speed of 10 meters per second. What's the acceleration as a function of x? Okay. Well, to do a problem like this, so can you picture what's going on? This particle is moving along this function. There's x and y. And I said it's moving in the direction of increasing x, which means it's moving this way along the path. And it's moving with a constant speed. We're trying to calculate the acceleration. Don't make the mistake of thinking that since the speed is constant, there's no acceleration. Acceleration does various things in 2 and 3 dimensions, right? It does change the speed, but it also makes an object turn. That's like what centripetal acceleration is, And so even though the speed is constant, we're going to see an acceleration for this. You with me on that? Okay. So, first, notice that the velocity vector is equal to the speed, I'll call that capital V, times a unit vector in the direction of motion. Well, coming up with the speed, we already have that. We were given that. Sometimes you'd be given that as a function of x also, or a function of the position component also. But we have to come up with that unit vector in the direction of motion. So how are we going to represent that? So to find a unit vector in the direction of motion, first notice that function notation you can also write in a vector notation, what's called a parameterization. The parameter that you're representing this position in terms of is x in this case. So first I'm going to parameterization of the function. Well, we know that we have this function relationship y is equal to x squared, right? As a vector, we can write it like this. The position is equal to, what's the x component of the position in terms of the variable x? Yeah, exactly, perfect. And what's the y component of the position?
X squared.
X squared, yep. So this is our parameterization, and it's called a parameterization because the parameter that it depends on, there's a parameter that it depends on, in this case it's x. Okay, well, it turns out that with any parameterization, if you take a derivative with respect to the parameter, it doesn't matter what the parameter is, it's going to give you a vector that's tangent to the path, which is what we want, in the direction of the parameter increasing, okay? So the derivative of p with respect to the parameter gives a vector. It's not a unit vector yet, so I'm going to write this as it gives a non-unit vector that's tangent to the path in the direction of the increasing parameter. So what does that mean about in the direction of the increasing parameter? Notice that here, well, the problem that I gave you, I said that this object is moving in the direction of x increasing. X is our parameter. Okay, so this will give us a vector that's tangent to the path in the direction of increasing x. Okay, that's what we want. The problem could have just as well said this thing is moving with a constant speed in the direction of decreasing x. Then it would be going the opposite direction. And all you'd have to do in that case is when you take your derivative of the position with respect to the parameter, just multiply everything by -1 at the end and it switches the direction. Okay, so we'll do an example like that too, but okay, so I'm going to write this as a vector u. You know, what we want is that unit vector that's tangent to the path. We're first going to start with a vector that's not a unit vector, but it's in the direction of the object's motion, and then we'll just divide by the length to make it a unit vector. Okay, so this is equal to, we're going to take the derivatives of p with respect to x, and so we get 1 for the x component, 2x for the y component, And so what that does is now this is the path, and at any x, this gives you a vector in this direction. Okay. If you plug in x equals 0, that's at this bottom one here, right? You get a vector of 1, 0, which is horizontal, which is what you would expect there. You with me on that?
That is a unit vector.
That one is a unit vector, but nothing else is. Okay, that one is a unit vector. So in general, I mean, think of x equals 1. Think of like this vector here when x is equal to 1. The direction there is 1 in the x direction, 2 in the y direction. So it's something like this. Okay, so it sort of makes sense. But you can see that 1, 2 is not a unit vector. So we have to normalize it. We have to divide it by its length to make it a unit vector. Okay, so to make this a unit vector, we figure out the length, the magnitude. That's 1 squared plus 2x squared square root. And so that's equal to the square root of 1 plus 4x squared. And so a unit vector in the direction of motion is, we're going to divide both of these components by the length. So we have 1 over the square root of 1 plus 4x squared. And then for the y component, 2x over 1 plus 4x squared. You could also write this as 1 plus 4x squared to the negative 1/2 and 2x times 1 plus 4x squared to the negative 1/2. Now that we have a unit vector in the direction of motion, we can write the velocity vector as the speed times that unit vector. In this case, we're using a constant speed of 10 meters per second. So this is just going to be 10 times 1 plus 4x squared to the negative 1/2. And then for the y component, 20x times 1 plus 4x squared to the negative 1/2. That's kind of a messy expression, but now what we've done is we've expressed the velocity vector in terms of a position component, and now we can do what we know how to do to find the acceleration. Okay, are you with me on that? So all of these steps have all gotten us back to the starting point of the chain rule problems we've done so far. Okay, and so now to calculate the acceleration, now we can say, so let me just write, this is our previous starting point. Let me say it like this. This is the starting point of these chain rule problems.
So we're not gonna take the derivative yet.
We are now going to, because, so if we're trying to find the acceleration, well, what did I ask in the problem? Yeah, what's the acceleration vector? So now to find the acceleration, now the acceleration is dv dx times dx dt. Okay,
So we have position, velocity, acceleration.
yeah, that's right. And so now we have to take this kind of horrendous derivative. So dv dx is negative 1/2 times 10 times 1 plus 4x squared to the negative 3/2 times the derivative of this stuff inside the parentheses with respect to x. So that's times 8x. And the y component is a little messier than that because we also have this product rule. So we have 20 times 1 plus 4x squared to the negative 1/2 plus 20x times negative 1/2 times 1 plus 4x squared to the negative 3/2 times 8x. Obviously, you could simplify that some. So let's say, so negative 40x times the quantity 1 plus 4x squared to the negative 3/2. So that's the x component. And the y component is 20 times 1 plus 4x squared to the negative 1/2 plus there's a negative there, so minus 80x squared times 1 plus 4x squared to the negative 3/2. That's dv dx. We're almost at the acceleration now. Dx dt is the x component of the velocity, which is this thing, 10 times the quantity 1 plus 4x squared, 1 plus 4x squared to the negative 1/2. And now just multiply them together, and the acceleration vector as a function of x is equal to, I'm not multiplying this out, but negative 40x times the quantity 1 plus 4x squared to the negative 3/2. X component is 20 times 1 plus 4x squared to the negative 1/2 minus 80x squared 1 plus 4x squared to the negative 3/2. All this times 10 times 1 plus 4x squared to the negative 1/2. Okay, so how is this different than problems before? I mean, the only thing that was different was we had to express the velocity in terms of the position component ourselves. And we had to do that by finding a unit tangent vector and multiplying it by the speed. Once we did that, it was exactly the same as previous problems, except that the derivatives were uglier because those unit vectors lead to ugly derivatives. Okay, but conceptually, I mean, it was exactly like that. Question?
What about the problem is telling me multiply by the x component of the velocity?
Yeah, that's the whole chain rule thing. That's like its catchphrase, you know? Like if that little baby on Who's the Boss was the chain rule, it would have said this instead of that's so rude, you know?
Yeah, that makes sense.
It's a little current pop history joke for you on a 37-year-old horrible sitcom. So yeah, anytime you're getting to a point where you have velocity expressed as a function of a position component, you know you're gonna have to use that chain rule thing. Yeah.
They said to solve it for y, would you write the function as a function of y and then?
Yeah, well, you couldn't do it in this case, notice, because you can't write x as a function of y. If you had half of this curve, you could, you know?
Yeah.
And then, yeah, you would do it the exact same way. You would have y in your, y component of your parameterization. You'd have square root of y in your x component. And then you'd go, when you did the chain rule, once you expressed the velocity as a function of y, here you'd have acceleration is equal to dv dy times dy dt, and you'd be multiplying by the y component of the velocity.
Does this work in 3D too?
Yes. Mm-hmm. One of the problems, I think like maybe the nicest, these always come out sort of ugly like this, but the least ugly thing you can do is a, what do you call it, a helix. Okay, some things drop out nicely if you're dealing with a helix. So there's a problem where you're doing a helix, this thing's moving in a helical pattern, and you're gonna calculate the acceleration. Okay. Let's plug in, let's plug in one value just to make sure this makes sense. You can think of this acceleration as having two components. For a second, instead of thinking the x and y components, let's think of a component that's tangent to the path. That's the part of the acceleration that makes it speed up or slow down. And then a component perpendicular to the path, that's the one that makes it turn. Okay. Well, since this has a constant speed, we won't ever have any tangential part of the acceleration. Okay. And so this acceleration is always going to be just perpendicular to the path wherever you are. So let's plug in x equals 0 and figure out the acceleration right at this point. And we know it should be just totally in the y direction if we did our calculations right. So I'm going to plug in x equals 0. And we get that ax, when x is equal to 0, the x component is obviously 0 there. The y component is 20 minus 0. And then we're multiplying it by 10. And so we get a total acceleration that's equal to 0, 200. Okay, so 20 Gs or whatever. Any questions about that? All right. The last topic in particle kinematics in a non-rotating coordinate system is circular or spherical motion.
I have a quick question.
Yeah.
So we have this path and like the acceleration doesn't depend on mass.
Right.
And so like a parabola is obviously like the acceleration due to gravity.
Well, you could think of it as a, I suppose since,
Well, here we have constant speed.
Yeah.
Constant acceleration.
yeah, right. It's, so if, for this to be a constant upward acceleration, you would have to have a parabola in the, in like the y position versus time, not in the y position versus x.
Okay, so it's totally different, and that's why
Yeah.
our acceleration is so much higher.
The acceleration is higher just because of how fast I said it was going. You know, if I had said that constant speed was 100 meters per second, this acceleration would be that much bigger. You know, remember that this isn't a circle, but if you thought of this as sort of circular motion, okay, just to wrap your head around what's going on, remember that the centripetal acceleration is v squared over r. Okay, and so if you have a relatively tight radius like this and a big velocity, then you're going to have something big squared divided by something small, and you're going to get a big acceleration.
And what happened to the mass? It just
Well, remember that we're just doing kinematics. So we don't care about masses yet.
Okay.
So the acceleration doesn't have anything to do with mass. It just is like you can imagine, a position is a function of time, doesn't have anything to do with mass. It just has to do with what the thing is doing, you know? And then you're just taking two time derivatives, so that can't have anything to do with mass.
Yep.
But acceleration should make your brain start to think about masses and forces and stuff, because why do we even care about the acceleration? Like, think, so we came up with the velocity as a function of x or as a function of y. Like, why would we particularly care about the acceleration? Because acceleration is the way that you go from kinematics to kinetics through Newton's laws. Okay, like acceleration is the only way to go there. Think of like, you go to the Mall of America, you know, and it's freezing cold and you want to take the Skyway from the parking ramp to the thing. Well, the Skyway is on floor 2. That's the acceleration, you know. So if you park on floor 7 and you want to get to floor 7 in the Mall of America, first you have to take the elevator down to the Skyway. And that's what acceleration is. No matter what's going on with the kinematics, first you got to go to the acceleration, then you take the Skyway, and then you can calculate whatever forces and stuff. Okay, Newton's second law is the Skyway. Okay. Any other questions about this? The main thing I want you to remember is the messiness of it all obscures the simplicity of it. You know what I mean? So don't get carried away on how ugly the derivatives are. You can do those derivatives when you get to them. Mainly, what you need to remember about this is if you're given a parameterization, or you can start with a parameterization of the motion, you're trying to calculate velocity as a function of that position variable. Once you have that velocity, then you're using the chain rule. And it's a two-step thing. It's just those two steps are pretty ugly usually. Okay. Okay, so circular and spherical motion. So these are motions where the particle is remaining a fixed distance from some point. And that point is the center of the sphere or the circle. The circle would be in 2D and the sphere would be in 3D. When you did this in Physics 1, most likely you probably focused more on circular motion, first of all. And then you thought about a tangential acceleration, thought about what direction that was at a single spot, thought about the centripetal acceleration, and you did all these directions kind of intuitively. You know, you looked at the circular shape and said, okay, centripetal acceleration is toward the center, tangential acceleration is tangent to the circle. Now, using vector calculations, all of those directions are going to be done for us. So it's a really nice, simple, clean way to do these calculations. Before we get into the calculations, I have to give a definition of the angular velocity. How many of you have used the right-hand rule in classes before? You've seen that before, most of you. Okay, well, the right-hand rule is a way to relate a rotation with a linear direction. Okay. Okay, right-hand rule. So you can think of it as a relationship between a rotation and a vector direction. So if you, so here's your right hand. Okay. Your thumb is pointing in the vector direction. Your fingers are showing a direction of rotation. Okay. And so a lot of times when you have rotational quantities, you represent their direction with that right-hand rule vector direction rather than there's no real clear way to represent a rotation. So instead you represent it with that thumb direction, okay? So the angular velocity, it's a vector. And it's given by the Greek letter omega, the lowercase Greek letter omega. And it is the rate of change of the angle around the circular path with respect to time in the direction of the right-hand rule.
Always.
Yeah. So like, for example, if you have, let me see if I can draw this. So let's say you have a coordinate system like this. And you have an object that's traveling in a circular path like this. So the way I'm visualizing this is it's going back into the page to go up and then circling around to the front of the screen to go down, okay? So if that is the circular path that the object is moving in that instant, let's say we're given that this is equal to 5 radians per second, okay? Then omega, the angular velocity vector, is going to have an x component of 5 and zeros for the others. Okay. One thing I want you to notice is for objects moving in the xy plane, what's the component that's non-zero? There's only one component of an angular velocity that's non-zero. Z, yep. So for objects moving in the xy plane, only the Z component of omega is non-zero. Then the angular acceleration, the meaning of that. We'll denote that with the lowercase alpha, like a goldfish vector. And this is the time derivative of the angular velocity with respect to time. One other thing I want you to notice about that, for circular motion, that's two-dimensional motion, omega and alpha. Come on. Omega and alpha are parallel. For general 3D motion, they're not parallel. There's no necessary relationship between their directions. So for general spherical motion, they don't have to be parallel. Okay, so now, given that, these are the two equations that you need to remember for circular and spherical motion. So for any circular or spherical motion, the velocity vector is equal to omega crossed with r. I'll define this r carefully in a second. And the acceleration vector is equal to alpha cross r plus omega cross the quantity omega cross r. Where r is the vector from the center to the object. And so notice that this is just the vectorized form of what you used in physics 1. This term is the tangential acceleration, and this term is the centripetal acceleration. Okay, but all the directions work out for you. And we're going to use this all the time, and so I have a memory device for you here. All ripe watermelons will rot. Sort of a pessimistic view of things, but it'll help you remember to put these all in place. So the alpha is an A, all ripe watermelons will rot. Okay. And you can remember the grouping for these. You have to group it this way, because what would happen if you grouped omega cross omega first? You get 0 if you cross something with something parallel to it. So you get 0 and this whole term would go away. Any questions about that? Okay, I will, I think the problems I'm going to give you are just going to be chain rule related stuff. So we'll do more about circular motion next time, do some example problems and stuff. Okay, that's all.